Hello, my name is Prisha, and today we're going to be talking about exponent rules. Today we'll be going through all the exponent rules, including negative exponents, dividing and multiplying exponents with the same base, raising exponents to a power, fractional exponents, and a couple of hard problems at the end just to test yourself. With that said, let's get started. Okay, so what is a negative exponent? When you see it, it'll just look like a regular exponentiated number with a negative sign in the exponent. But that negative sign does not mean that the number is negative. Instead, it means that the number is equal to the inverse of itself with a positive exponent. For example, 3 to the power of negative 6 is also equal to 1 over 3 to the power of 6. When you're dividing or multiplying exponents, especially dividing, you'll actually see this a lot. Some questions might let you leave an answer with a negative exponent, but it's more likely that you'll get a question that asks you to only have positive exponents in your answer. Knowing this would help you simplify your exponents into something more easily understandable. Now, let's divide some exponents. First of all, what does the same base mean? Well, that just means that the base numbers of the two exponentiated numbers, in layman's terms, it's just the bigger number, as you can see here, are the same. And once you verify that, you can simplify an expression like this example here by just keeping the same base and subtracting the exponents from each other. For example, here the answer would be 3 because we'd keep the base as 3 and we'd subtract 3 from 6, giving us 3. So we'd have 3 to the power of 6 divided by 3 to the power of 3 just equals 3 to the power of 3 because 6 minus 3 is 3. But here, what happens when we have something like 6 minus 7 where we'd get a negative number? Well, that's where our negative exponents come in, and this is a proof of why negative exponents work the way they do and why dividing exponents works the way it does. So if we expand this out into 6 threes at the top and 7 threes at the bottom, I'm not going to draw them all out for the sake of time, but I'll just draw a couple. Remember, you're multiplying in between. Well, if we wanted to simplify this expression with some of the canceling knowledge that we have before, when we cancel the numerator and denominator, we can cancel 6 threes from the top and 6 threes from the bottom. And since there were originally 7 threes on the bottom, we're going to end up with 1/3. What also equals 1/3? 3 to the power of negative 1, which is exactly what you would get if you subtracted the exponents. You get 6 minus 7, which is negative 1. And that's why negative exponents work the way they do, and that's why dividing exponents like this works the way it does. It's just a simpler way of thinking about it without having to write out everything and cancel out everything. But now what about this third example, where we have 3 to the power of 6 divided by 3 to the power of 6? Well, if we use our dividing exponent method, we'd get 6 minus 6, which is 0. So the thing to remember is that anything to the power of 0 is automatically 1. And we can obviously prove this because since we have the same thing in the numerator and the denominator, this expression is equal to 1. That's how it is with all fractions. So that's another small proof to prove why things to the power of 0 equal 1. Now let's try multiplying exponents. It's essentially the same concept as dividing, but you're going to add the exponents instead of subtracting. For this first example, we're going to keep 3 as our base, and we have 6 and 3, so we're going to add them. So 6 plus 3 is 9, so our answer is going to be 3 to the power of 9. And again, this can be really quickly proven if we write out all those 3's. Again, I'm not going to write them out just for the sake of time, but I'm just going to do a quick representation. And you'll notice that you're actually multiplying everything together because 3 to the power of 6 is essentially multiplying 3 by itself 6 times, and 3 to the power of 3 is multiplying 3 by itself 3 times. So if you combine that together, you're multiplying 3 by itself 9 times, because you're just adding the amount of times you're multiplying 3 by. So that's why that's 3 to the power of 9, and that's why this multiplying method works. And for this next example, we have 3 to the power of negative 6 and 3 to the power of 7, which would essentially give us 3 as our base, negative 6 plus 7, which is just 1, and again, any number to the power of 1 is just that number. This would just be 3. You can leave it as 3 to the power of 1, but it's just better to leave it as 3, to be completely honest. It's simpler, and that's the name of the game with these types of exponent problems. Okay, now it's time to raise exponents to a power. Again, concept is very similar to multiplying and dividing exponents, but we're just multiplying the exponents now. So for this first example, we're going to end up with 3 as our base, just like always, and we're actually going to multiply 6 and 3. So we multiply 6 and 3, we get 18, so our answer here should be 3 to the power of 18. This can be proven because, remember, anything to the power of something is just itself multiplied that many times. So 3 to the power of 6 to the power of 3 also equals 3 to the power of 6 times 3 to the power of 6 times 3 to the power of 6, which, if we recall our multiplying rule, we just add all those 6's together, and that gives us 18. So again, quicker way to go about it. This also works with negative numbers. We get 6 times negative 3, which is negative 18. So we'd get 3 to the power of negative 18, or 1 over 3 to the power of 18. Oops. Well, that's a little bit of a bad exponent, but 3 to the power of 18. And the interesting thing about this third example here is that it actually combines both the raising exponents to a power rule and also the multiplying exponents rule. So if you see 6 here, we can recall that 3 to the power of 2 is actually 6. Because with these types of expressions, we always want to try to get to the same base, because that's when we can use our multiplying exponents rule, and that's what makes everything really easy. So if we regard this 6 as 3 to the power of 2, we can have 3 to the power of 2 on the inside, and then to the power of negative 6 on the outside, which means that we can use the power rule here and then use our multiplication rule. So we'd have 3 to the power of negative 12, because 2 times negative 6 is negative 12. Sorry for the slow writing, but we'll get through it. And we'd have 3 to the power of 7. Negative 12 plus 7 would be negative 5, so our answer would be 1 over 3 to the power of 5, or 3 to the power of negative 5. Yep, and again, you can use this type of logic thinking for any sort of problem where the bases are different, but they seem like they're powers of each other. So you could do this with bases of 4 and 2, because 4 is 2 to the power of 2. You could do it with bases of, let's say, 32 and 2, again, because 32 is just 2 to the power of 5. So make sure you can think of problems this way. You always want to get to a common base, especially when you're multiplying and dividing, because that makes it so that you can use your rule and it makes the calculation much easier. And now, finally, fractional exponents. A fractional exponent is essentially the same as taking the root of something. For example, 3 to the power of 1 over 2 is just the square root of 3. Likewise, 3 to the power of 1 over 3 is just the cube root of 3, and so on and so forth. You can take the quartic root, you can take the quintic root. It goes on for all numbers. But what if we have something other than 1 in the numerator? What do we do with that, like 2 right there? So in this case, we'd do our same radical like before, and we'd use that bottom number, the denominator, as the number that goes over our radical. So in this case, this would be a cube root. And then that numerator, we're actually just going to put it under the radical. We're going to raise what's under the radical to the power of the numerator. So we're going to get 3 to the power of 2, and that's all cube rooted. What I want you to remember here is that everything that's under that radical is going to get that numerator number. So for example, here I have 3 times 6 to the power of 2/3. Instead of just having 3 to the power of 2 here, I'd have 3 times 6 to the power of 2. I would raise everything under that radical to the power of the numerator. And the way I like to think about it, the way I like to remember that, that 3 is going to go above the radical and that 2 is going to go under the radical, I think of the 3 as a balloon. I think of the denominator as a balloon and the numerator as a stone. Numerator sinks below the radical, denominator floats above the radical. They kind of switch places. And that's just the way I like to think about it. You can come up with your own ways, but I always find it helpful to categorize or to remember your strategies as something fun or something that's a little bit weird or interesting, because that makes it stick in your brain. And that's really it applies to anything. And now it's time for a hard question. So we have 2 times a times b to the power of 3 over 3m to the power of 2, all to the power of 3. So the way I'm going to go about this is I'm first going to take that 3 from the outside and apply it to everything within. So I can take that 3 and I can apply it to each number in here because they're all multiplied together. So I'd have 2 to the power of 3, that would be 8 up here. A to the power of 3, that would just be a to the power of 3, nothing special. And now we have b to the power of 3 to the power of 3, that's where we'd use our power rule, and 3 times 3 is 9, so we'd have b to the power of 9. And then down here, we have 3 to the power of 3, that's 27. And we have m to the power of 2 to the power of 3, again, another time for our power rule. So that's 2 times 3, so m to the power of 6. And note how with these problems, either the numerators are all different or the denominators are all different. In this case, both are different in each answer. And technically, if you're running out of time, you can get away with just doing the numerator, checking through all your answer choices, and picking the one with the correct numerator. Because chances are, if you're pretty confident in how you did the calculations for the numerator, that's going to be the answer, and you don't even need to calculate the denominator. Again, I only suggest this when you're running out of time. It's really just a strategy to quicken things up, but in any other scenario, I suggest you just do both parts just to be completely safe, because it could turn out that you did the numerator wrong, you got the denominator correct, and you realized your mistake when you were looking through the answer choices and you fixed it. So I always just take that precaution. But in this case, the answer is E, and that's how that works. Oops. Next problem. We have 1 over a to the power of -3 to the power of 4. So this looks like something for our power rule to do. So we'd have 1 over a to the power of -3 times 4, which is a to the power of -12. So this is an interesting situation. We have something to a negative power, which is usually supposed to be 1 over this to the positive power, over 1. So let's actually go through the entire thing, and I'll tell you how to think about this. So we have 1 over a to the power of 12. If we remember our division rules, we're going to multiply by the inverse of this. So we're going to have 1 times a to the power of 12 over 1, which is just a to the power of 12, and that is our answer. So the reason why this is just because that negative sign, it's really just meaning that it's the inverse. So you don't always have to think about it as 1 over the positive power if you just see this. You just want to think about it as flipping the fraction. So if you see 1 over a to the power of negative 12, you'd flip the fraction and you'd get a to the power of 12 over 1. And we just change the sign. So that's how I like to think about kind of what it means to be an inverse. And as you can see, a to the power of 12, that is e. So that's right there. Okay, thanks for listening and have a wonderful day.